is Shen from Ningbo University, and he's going to talk about Vortex confinement.
Thank you. Thank you for the introduction, and be very happy here to share the work. So this is a work with Professor Slim Ibrahim and two of my students, Qingwei and Chen Shi. So we start with some quick introduction on the 2D ERLA. So we all know the 2D 2D ERLA in the simple connect domain is written by this way, and especially on 2D, the vorticity can be written in this 1D scalar form, and it is transported by the flow. So the vorticity can be recovered through the velocity can be recovered through the Biot-Savart law, and the key here is we need to know the boundaries, the domain's Green's function, and the domain's Green function usually we can split into two parts. So one actually is come from the whole domain, and the other part is smooth. So how to characterize this G omega, basically the gamma omega? We need to know how to describe the boundary. So thanks to the Riemann mapping theory, so there exists conformal maps. So map this omega into unit disk. Okay, so we know the unit disk Green's function, and then we know the Green's function on a general domain. So this is a composition of Green's function on the unit disk and the and phi. Okay, so basically now we know everything if we know phi. Okay. Yeah, phi is conformal map. Okay. Sorry. So there are some for the 2D ERLA. There are some various classic Will-Posner results starting from 1933. And for the unique weak solutions with boundary vorticities by Yudovich in 1963. And for them, the global existence and the weak solutions, so they're famous, the L1, LP vorticity by Dupre and Maeda. But the uniqueness we are not known. We don't know the uniqueness. So for the vortex sheets, so the existence is done in 1991, and there are many other solutions called the mild solutions. So here, our interesting thing is now if the vorticity is highly concentrated in some blobs, so how this blob go expand? So they might expand, right? They might leave their center. And the support may grow bigger and bigger. Okay. And the very natural thing is we can image a direct mass. Okay, we can consider the vorticity like a direct mass, but the direct mass is not a vortex sheet. However, we can, if there are many direct mass together, we can consider vorticity as a summation of the direct mass. This will lead to this the point vortex system. Okay, so the point vortex system is introduced by Hermos in 1867. So the vorticity as a summation of a Dirac. So AK is like now the strength, vorticity strength. When you plug in the 2D equation, so formally we can write down the equation of the vortex dynamics. So this is so here this long equation, Okay. And these equations are called the Kirchhoff-Rosse equation. So the point vortex system is a very good new approximation of the earlier system. So actually in 1990, so Goodman, Hall, and Rograb, they proved a very nice numerical approximation scheme there. And they said that if you have vorticity, it's not necessarily concentrated. You consider there are many point vortex there, and there will be a very good approximation. And then we also have many convergence result. So like starting from here, from here to 2019, there was a strong the weak convergence and a strong convergence. And also there are some results about the central configurations, like in embodied problems. So these guys, Shengyi, Shu Qiangzhu, and they work on embodied problems, but they still do something on the point vortex for central configuration. Okay, and here I want to mention that although the configurations lead to the point vortex, they will collide at some inside the domain, but these cases actually are rare. So it's barely happen. And especially in 2022, Donati he shows the global existence of endpoint vortex system. So in a boundary domain, almost they're almost true for every initial data, almost for every initial data. Okay. And for the confinement thing, vorticity confinement. So this study is coming. I think as far as I know, it starts from Machilo and Prevri-Brinti, sorry, in 1993. So they proved that if you have a bunch support of omega 0 included in the unit disk, many unit disk, and omega 0 is a single sign. So there are a lot of blobs, and one of them maybe some blobs are positive, some blobs are negative. And omega 0 is not too large. So basically this means that the L1 norm of each block is like constant. Okay, then in this case, they can see that for any time t, but less than the blob time, okay, they need to make sure that the point vortex system makes sense. And then for any delta, there is a small enough one, so it depends on the t and delta. We have that omega t is still included in these domains, in this moving disk. So DIT is the solution for the point vortex. So basically, you can see that the blobs move with point vortex, right?
What do you mean the zero is not large?
Yeah. This means you basically each blob you have like a L1 norm of each blob is like 1. Yeah, you can consider this something like that.
Omega.
Yeah.
But isn't omega 0 sum of Dirac?
No, omega 0 is not Dirac. This is a blob. It's a vorticity. It's not Dirac. But Zi, this is a Dirac. This is a point vortex, position of point vortex. So this means that if you have many blobs, so in the one blob center is like point vortex. So the blob will move with the point vortex. So the blob moves and point vortex also moves. So it's like they are very similar, these two systems. Yeah, of course. Omega 0 will move. It might move. It may move, right? It's involved with time. You have maybe sometimes here and after some time it become bigger. So for this data, I think this data is like a threshold. The threshold less than the epsilon is less than this data, you can find something. The threshold. Okay, so but this is like a fixed kind of component. Basically, you give t, you give epsilon. Say okay, we have something, right? But now, what we are interested in is we call the long time confinement. So how this time t depends on epsilon. Okay, so this is a long time confinement. Okay, for a long time confinement generally is formulated in the following. So these conditions are the same. These three conditions same, but how here now you define the exit time from the disk in this way. So the previous result saying that when epsilon goes to 0, this exit time will go to infinite. Okay, so how long this t epsilon, how large t epsilon can be? So this is for the vorticity confinement problem. Okay, so in 2018, Buta and Machilo, they proved that in R2 and in the general case, if you have several point vortex and the general case, then this time has a lower bound. It's a log epsilon. And in the case of a disk, and the disk is centered at 0, so a single vortex blob located around the center. So this time can be increased to epsilon to the power minus alpha. So we call the power law. So alpha is some constant. Alpha is some constant. It's like I think it's less than 1/2. This is the constant. But you can see this time is much longer than the log time. Okay. So you can see that some it usually depends on the domain, or it depends on the regions where the fluid where the equation holds. Okay. So for some domains it will make the vorticity like stay confinemented, and for some domains it will speed up the spread of the vorticity. And in Donati and Iftimi, they in 2022 they extend the second statement to slightly more general simple connected domains. So they have a condition therefore on the conform map. Okay. And now for us, we actually are interested in a easier case. So we considered like the point vortex system. So for the point vortex system, the confinement are now reduced to like the stability problem of the point vortex system. So, but the stability problem is not everywhere stability. We will consider stability around the stationary, we call the stationary point. So the stationary point is what? This is for a single point vortex. At that point, does not move. So this is a one point vortex system. So basically, the stationary point means the right-hand side equal to 0. So according to this result, the stationary point will always exist. Okay, and we can say that a single point vortex always exists globally. So, and you can say x0 stationary if and only if phi double prime equals 0. So this is some known result, and we can study the stability of just a one point vortex around this stationary point. So this is the result. If you have this comparison between primes cubic and the triple prime, the first case that we say is stable. So for one point vortex is stable. So the exit time like it's infinite. So it always go around the center around the stationary point. And the other case, it is unstable. So we can calculate that this time is no longer is no better than log. So basically, there was a one direction that will go away from the stationary point exponentially fast. So that's why you will have this log of epsilon at most. Okay. So for the point vortex system with boundary, we careful about the integrable part. Like it's different from if you compare this in the whole domain. In the whole domain, like the endpoint vortex system is basically integrable for n equal to 1 to 3. This is because you have 3 independent conserved quantities. So you have conservation of interaction, conservation of energy, rotational symmetric, like these metrics. But when n is bigger than 4, these metrics basically you don't have any other conserved quantities. So usually n bigger than 4 it's not integrable. And if you now introduce the boundary, so you will break the symmetric of the rotation and translation. So usually you only have the conservation of energy. Then even for 2-point vortex system on the bounded domain, it's not integrable. So these guys they show some kind of chaos phenomena will happen when n equal to 2, even for n equal to 2. Okay, so what we do recently is we prove that if the boundary, if the domain basically satisfy this stable condition, so we can say the domain is stable, then for almost every initial condition that's close to the stationary point, of course, we should have another condition that A1 plus A2 is non-zero. So the strength of them is sum of the strength is non-zero. Then we can say that these 2-point vortex will never go away from the stationary point. So you can say the T epsilon like goes to infinite. But this one is not for every position near the stationary point. We can only say it's almost every station, almost every. Okay. And for the borderline case, if you take equality, then the result is weaker. So you allow it may go away from this slightly bigger ball, and the lower bound time is like epsilon to the power negative alpha. So you got power law. It's not infinite now. Okay. And here again, we need the condition that the sum of the strengths is non-zero. So if you see sum of strengths is 0, then usually we don't expect some confinement. Or we can say it's always unstable for the stationary point. So this is one example. So if you consider the system on a disk, so you can explicitly write down the solution. So this is A1 equal to minus A2 equal to 1, and Z1, Z2 has two position has some symmetric. And now we can plot this trajectory. You see, they will leave the stationary point 0 very fast. They just leave away. They just go away. Yeah, it's just go away. Okay. Okay, what's remaining is like for some maybe measure of 0 initial condition that close to station point. What happened for them? So they will slowly go away from the stationary point, but and we can again calculate this time. So this time is like epsilon to power negative m. This n is you can fix it earlier. Okay, if you fix n very large, for any fixed n very large, you can always find this constant Cn such that okay the Ck does not go far away from the stationary point, or we can say Zk does not go far away from its initial position up to this time. Okay.
So in this case, you don't need to exclude the set.
No, this is weaker if you consider that. It's not all-time confinement, right? But this is like the remaining part. You have some points that does not satisfy some we call the diphonon condition, and then these points will slowly go away from a stationary point. Okay, it's slightly weaker. Okay, and what's okay? Sorry. So this is like for n equal to 2. Okay, basically we are done for that. And for now, when we increase the number, say n equal to 3, so things become more complicated. And for n equal to 3, basically you can, on one side, you can consider n equal to 3 as just the perturbation of the of the 3-point vortex in the whole domain, because if you add boundary, the boundary is like perturbation if you consider 3 points are around the stationary point. Okay, and there are some configurations very interesting. It's like the total thing will behave like the 2-point vortex. So you see two of them will rotate from each other, rotate around their center of vorticity, and the two of them as a whole part together with the third one, they will behave like 2-point vortex. Okay, so here we have we can have a I don't know if you can see that. Okay, these are two examples. So the 2-point initial point, I think I have a dot here. This stands for the initial point. You see the red and the green one, they're close to each other. They are very close to each other, right? So they will rotate around their center. Okay, like 2-point vortex system. And now these two points you consider as the 1 point. And now with the other one, the other far away from them, they will move like 2-point vortex system, right? Very interesting. So here, of course, we still need some like a non-degeneracy condition that the summation of this of the strengths is non-zero. So if the summation of strengths is 0, again, they will behave like 2-point vortex. You see, the first two, they are rotated from each other, and the other one, together with the third one, they are not. This is like 2-point vortex because the summation is 0. So 2-point vortex, if the summation is 0, they will move parallelly, go away from the stationary point. Okay, and of course here I didn't plot the boundary because the boundary is I think it's like size 1. This is like the size 001. It's a very small. Okay, so now we want to explain this phenomenon basically. So to do that, it's a good tool is now we start with the Jacobi coordinates. So this is a Jacobi coordinates is a very popular in I think in model problems. So it's like a relative coordinates. So this is a definition, and if you take 3 points, 3-point vortex, Jacobi each coordinates means like this way. So omega-1 is the distance between the first two points. Omega-2 is the third one minus the center of the first two. Okay, and omega-3 is the center of the 3-point vortex, just the center of them. Okay, so under this coordinates, we can explain what happened like in the previous pictures. So this is the major result. We require that the first two, of course, is non-zero, summation of them is non-zero, and we require that the 3 points summation of 3-point strength is non-zero, and we need the stability condition. Okay, so we say that the first one, W1, you can see the distance between the first 3 points is much smaller than W2. This is the you can see what is W2. Yeah, W2 is this one. So the red one, the distance of the red is much smaller than this green one. So it's like now you go back to this case. So this one, the distance of these 2 points much smaller than the distance between them and the third point. Okay, and the center of vorticity. Okay, this condition is a much relaxed. I think it's less than epsilon is enough. Okay, even it's bigger than, slightly bigger is also fine. Okay, so here for convenience, we say it's less than epsilon. Okay, so the result is now the distance HW, they will not go very far away from its initial length. They will still stay close to their initial state up to some time, up to this power of time. So here n, we need n, like if you can see this, if it's n bigger, then this is a very large time. This is because lambda is bigger than 1, and when n bigger, this the power is positive, so it's a very large time. Okay, so the tools we use to prove it is the very famous Birkhoff normal form, but not a very standard one. So when we go to there, I want to introduce something about the Lee transformation. So this is a standard tool that to create the canonical transformation. Like if you have a G as a if you have a polynomial, if you have a function or polynomial smooth, then you can write down this Hamiltonian system. So xg is a Hamiltonian vector from G. So and if you define the time one map of this flow, this will give you a Lee transform. This is a Lee transformation, and this transformation is a canonical. And here you can also calculate this one. So f, like a general function, you compose with this the Lee transformation. So you can expand this as a series, infinity many series. So this break is a Poisson break. Okay, so when you have Lee transformation, then we go to we can review a little bit around of the classical Birkhoff normal form. So the classical Biot form, usually we apply this to the classical mechanics. So for the classical mechanism problem, the Hamiltonian is usually like this one. So you have a quadratic terms. So this alpha k bar is something, so the variable. You have a quadratic part. Though this part only, it's like this is an integrable system. And now you have a other perturbation, small part. So you have terms with a degree more than 3. It's a polynomial. Okay. And the Biot form will put the Hamiltonian into this form, like this form. So this is the goal. Every time you apply the normal form, you apply the canonical transformation, you will delete, you will cancel one higher order terms and push the remainder to more higher order degrees. Okay, and now you leave the H0 unchanged. And what else is you have something that you can never cancel. So these things you can never cancel is we call the resonant part. So this resonant part is a function of action variable only. So it's always like a function of alpha 1 bar, this is the whole part, and alpha 2 bar up to alpha n bar. So this alpha 1 bar, you can consider this as an action variable. So dk is only a function of action variable. Okay. So how do we do these steps? So usually we do it by induction. So if you assume that case step is okay, then you go to next step, and then you use the formula that we mentioned in Lie transformation. You can expand basically. So we focus on the lowest order term. So this is like this part is the lowest order term, the red part. Rk plus 3 is like this is the degree of k plus 3, and this one we want to cancel. So how do we find the next canonical transformation? So phi k plus 1 should satisfy this equation. Sorry, the gk plus 1. The gk plus 1 is a generating function of phi k plus 1. So once you have a generating function, you find the canonical transformation. So the generating function, ideally we satisfy this equation. And then you can cancel this one and leave the higher order terms. So you successfully go to the next step. Okay. And pitifully, this is too good. This is too good. This is too ideal. So usually, in practice, we didn't solve this perfect equation. We solve something like this equation. You have something that you can always have something that you can never cancel. So this is something that as we call the resonant part. So this part will never cancel in this procedure, and it's always stay there. But luckily, the resonant part is also fine because it's only depends on action variables. And these two, this is the formula, or or we can see this is a solution for this linear equation solution. We calculate this G. If you have this R3, which one Rk plus 3, which this is the thing that we want to cancel. This is given. Then we can solve for G in this way, and zk plus 1, the remainder part. Okay. So this is the classical procedure of the Biot form. So like now, if you follow this way, you can go to any order you want. Okay. But now our problem, now go back to our system. So we still need to write down the Hamiltonian first, then we want to apply the normal form. So for the Hamiltonian, now when n equal to 3, we use Jacobian coordinates W1, W2, W3, and for the third one, W3 actually is the center of vorticities. So in the stable case, we can write down the equation of W3. It's the linear part it's a standard rotation. So there is a transformation like you change W3 into theta 3, and theta 3 is a standard form. The rotation is a standard rotation. Okay, so we do this kind of transformation first from W to zeta, and then normalize it. It's we go to the normalized Hamiltonian, so written in alpha. Okay, now if you compare this to the Hamiltonian, the classical Hamiltonian, you will see we have the H0, so we say the unperturbed part is different. We have a log, we have two log. So one log actually comes from the comes from R2. It's a whole point. It's from the whole domain. Okay, and this is this quadratic terms come from the rotation of the center of vorticity, linear rotation, and you have other things here.
What's omega?
Uh,
Small omega.
this small omega is the rotated frequency, but it is known basically. It is a rotated frequency. It is known. Yeah, yeah. Because if you observe the equation of W3, sorry, I didn't write this down. The equation, the linear part of the of W3 is a rotation. So this this omega is the frequency of this rotation.
So it depends on the main.
Yeah, it depends on the domain. It only depends on the domain.
Okay.
Yeah. So it is known here. Okay. All these like this capital A or something, they are also constant. It depends on the strength of point vortex. Star position. Okay, so this is like the we consider this small h0 as this red part as the unperturbed part. So now the question arises: our Hamiltonian, you have a singular terms. When alpha 1, alpha 2 is 0, you have singular. This is one thing, and the other thing is our Hamiltonian is not homogeneous. So the class Hamiltonians are all quadratic; they are homogeneous. Now this is not homogeneous. So if H0 is not homogeneous, you see if you still want to solve this equation, okay? So the f is a homogeneous function, and H0 is not homogeneous. So this equation usually has no solution in polynomial. Okay, if you still want to search a polynomial solution, it's impossible. Okay, and the other consideration is this part, because now we consider. Yeah, I can point here. Okay, so now we consider this black part like should be a perturbation, right? Now this alpha, this is okay. They are called this one alpha 1 square, alpha 2 quadratic term. This one we can say it's okay. It's polynomial. It's compared to the log it's 3. It's small, right? But what about this part? The log 2 log part. Are they small? Are they still small? Okay. So this problem arrives. So how do we apply the normal form? So when we apply the normal form, it's non-standard. Okay. So this is the way that we try to apply normal form. So first we observe, we will let alpha 2 is bigger than alpha 1. So alpha 2, you can simply consider alpha 1, alpha 2 as just the W1, W2 in the normal form. Yeah, here. So it's a normalized of W1 and W2. So alpha 1 is the first distance, small distance. Alpha 2 is like the green part. So in the condition, so we say alpha 1 like W1 is much smaller than alpha 2. So here we use that. Okay. If you use that, then we can see that the previous one. Yeah. Now we can see these two log actually is we can expand this and we can see they are small. Okay. So to emphasize this phenomenon, we instead of working on alpha 1, alpha 2, when we measure the perturbation, we will see equation on this beta 1 and beta 2, beta 3. So in this way, now we can write the Hamiltonian, the major part, we can see the integral part, plus something small, but it is polynomial in beta, but not polynomial in alpha, polynomial in beta. Okay. Now what we want is to cancel this alpha k beta bar L. So k L these are multiple index. Okay. So to cancel that, we just explicitly calculate this break. So now we want to create a beta k beta bar L, and what else we can explicitly do that? Okay, but here you see we divide by k1 plus minus k L1. So this means this procedure can only true when KL is not in this I call the first resonance set. If it's not in there, then we can do this. What if KL is inside this resonance set? We can calculate another one. This is another equation, which can also cancel beta K, beta bar L. However, you see again the same thing. You divide by K2 minus K2 minus L2. So again, it's like we define the subset of the first resonant R2, RS2. As long as KL is not inside this, KL inside in RS1 but not in RS2, we can apply this formula to cancel this beta K, beta bar L. Okay, now the last case is that if it's in if KL is also in the second resonance set, we can reduce it to this. We can use this simple formula, simple calculation, directly cancel beta K, beta L. So K3 equal to L3, we call this the third resonance set. So you see, each resonance set is a subset of the previous one. So RS1 contains RS2 and RS2 contains RS3. Okay. Now, if KL is inside RS3, then you see all these quantity index, they are equal to each other. So this gives you the this gives the beta K, beta bar L. This is action variable. This is action variable. So this one we can never cancel. Okay. Okay. So this is the way that we solve the equation. So instead of solving the original equation, we have another one appears. So we don't care about the I think we don't really care about the details, but we focus on these degrees. You see, now things are complicated. Instead of solving equation, now we have a plus r. We have another one plus rk, and this rk here is a higher degree term. So it's here. So so this is something that you want to cancel beta K, beta L. This is like K plus the degree is K plus L, but you see the RK, the minimum degree of RK is K plus L plus 2. So it's like higher order terms. And ZK, okay, it's the same thing, it's K plus L. And the G now it's no longer homogeneous. It's now you have the worst case you have 3 terms. Okay, for some cases you may have a homogeneous one, but this one actually it's not bother us too much because it is a polynomial. It's fine. Now it's like now in polynomial space we already find the solution. We found the solution. So what we paid is now instead of cancel the higher order terms, we create another higher order terms. But the lucky thing is that it's much higher than the it's more higher order terms, we can say. Okay, yeah. We want to cancel K plus L, degree K plus L, but we create some terms that K plus L plus 2. Okay, so yeah, once we have this one, well, once we have this procedure, basically now we can start doing the normal form. And we doing normal form, next is we can prove the Birkhoff type theory for n equal to 3. So this theory, the Birkhoff type theory tells us that you can put the Hamiltonian into like the nth order Birkhoff normal form, like this one. You have the canonical transformation. Okay, you transfer the original Hamiltonian into the unperturbed one plus the resonant part plus the remaining part, and remaining part is much higher order terms. So here I measure the higher order in beta, so it's beta, the higher order of beta, and also you can measure the deformation of before and after the map. So something with prime, I say it's after the map. So this is after map. Without prime is before the map. So after the map, the distance does not change too much. So this lambda is for some technical reason. I think we can focus on this, the first line. Okay, this line is a little bit complicated, but it's not that too special. Okay, we can focus on the first one. You see the you see before map and after before canonical transformation and after the canonical transformation, these variables that do not change too much. Okay, so the canonical transformation here means the canonical transformation here is a nearly identity. Okay, so now this is the key theorem to prove the power law basically. And what's next is quite standard. So once you have this Birkhoff type theory, we can we can follow this standard step to prove the main result. So here the standard step first is like you can define the exit time. So in this way, so this is the domain near the stationary point. Like you consider as a radius, I is like a radius of the domain. Okay, and alpha t is a solution. So 0 is the initial condition. So you start with the initial condition alpha 0, and you fix some radius. So this tau means how long the point vortex will go. So how long the solution will go away from alpha 0. Okay, then you apply the Birkhoff type theory. What you get is now there is a canonical transformation. Blah blah blah. You can put the Hamiltonian into something we want. You have high order here, and then and you apply the Birkhoff normal form again on this inverse transformation to get the deformation estimate. To get this distance between alpha prime and alpha. It's something small. Okay. After that, we want to estimate this one. So the i's here means action variables. So the definition of I, you can see the definition of alpha is alpha times alpha bar. So alpha is I alpha is like alpha I times alpha I bar. So the I is action variable. Okay. So the meaning to estimate this part is that if we can successfully estimate this part, for example, if this is very small, means what? That means the initial W and the final W does not vary too much. Okay, because the alpha is like a W, alpha prime is alpha prime is like here. So alpha prime here is like a W0. Alpha is like a W. So at time t and at time 0, the distance does not vary too much. So then we can have the theory. Okay. So to prove this one, yeah, I think this I have a typo here. There should be no prime. There's no prime. Yeah. So it should be this one. So to estimate this one, you can split this inequality into three parts. So the first two parts are quite standard. So it's very easy, quite standard. We'll immediately get this. And the third one, you can use a definition. You use a dynamic system. Okay, it's an equality. And from the first equation to the second equality, it's here we use a canonical transformation. Use a Birkhoff normal form because H0 and the resonant part will cancel together with I. It is 0. So you're left with this Rn Poisson-Berg with I. Okay, and that's we can do this standard estimate. Okay, so next step is somehow we estimate this part. So we only have this part to estimate. Okay. So to estimate this part, I just here I take I equal to 2 for example. So the second one. Why I take the second one? Because the second one is a little bit special here. So usually it's all components are same, but here for our case the second component is a little bit special. because for beta 1, its definition of beta 1, we divide by alpha 2. So this means that we don't want alpha 2 too small. Okay, if it's too small, then beta 1 is very, very large. This is not good, right? But we can image the one alpha 2 cannot be too small because alpha 2 initially is like epsilon. It will not go to epsilon to some super high power because it is mapped by a canonical transformation, and this canonical transformation is almost like an identity map. So alpha 2 should not change too much under the canonical transformation. Okay, so that's why here we say I take I equal to 2, for example. Okay, so for this one we can first calculate this standard one, standard map. This is like for standard tour. We calculate this part, and we can see what when this term becomes biggest one. So because the dangerous part is beta 1 basically, because beta 1 is divided by a small thing, alpha 2, which is a small. Okay, so the worst thing is when all the index KL they all falls on beta 1. So you don't have anything on beta 2 or beta 3. So KL only have first component. Then we can say the worst case is in this case, and we can say that this one has a maximum like in here. Okay, so what's next? We want to estimate this part. So difficulty here is we need to make sure that alpha 2 prime does not go too small. We want alpha 2 prime stays like epsilon. We don't want alpha 2 prime stays like epsilon cubic. Okay, alpha 1 prime is something small. It's epsilon lambda. This is like epsilon. Alpha 1 prime is like epsilon lambda. Alpha 2 prime should stay like epsilon. Okay.
Question.
Yeah.
Is this beta a canonical?
Sorry?
Is this beta a canonical transformation?
No. You mean beta?
Beta, the transformation between alpha and beta.
No, it's not canonical. It's just to observe the how do we define the high orders? We define high order, or we say high degrees in terms of beta, not alpha. Okay, if you do in terms of alpha, then you cannot deal with this log terms. If you do in terms of beta, then you can deal with this log terms and expand this as polynomials. So here the beta is basically only used in estimate. For the canonical transformation, we will act on alpha. Yeah, act on alpha only. Okay. So this is the next goal. We need to make sure that alpha 2 it stays like epsilon. Okay. So here it's also the method is actually quite standard. So you can claim that for this is the claim. So we claim that for this t, for this kind of t, the I2 minus I2, so this distance, okay, is very small. It's like epsilon square. It's not epsilon. It's epsilon square. Okay. So if this is true, that means that the alpha 2 prime is like alpha 2 prime at 0. Alpha 2 prime at t is like alpha 2 prime at 0. So after some time, it does not change. There will be a lower bound. Okay. Okay. Now to prove it, it's standard by contradiction. You say that at t, assuming by contradiction at t is equal, then it is equal. Okay. So for t is less than, then we can solve this equation and see kind of lower bound and upper bound of I2, and now this implies a lower bound of alpha 2 prime, okay. Then we can derive contradiction. Once you have that, then you estimate this blah 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 blah, and I think at the very last you follow this one. This is a nature estimate. You follow this one. Eventually, you got wrong equation basically. Oh no. Yeah, I think yeah, here, sorry. Yeah, so eventually you got it here. So this is like tells me that epsilon squared is less than epsilon to some cubic plus. That's impossible. Okay. So alpha is like the original one. Alpha prime, you act on the action. You act you act on the canonical transformation. So after canonical transformation is alpha prime. After canonical transformation, alpha prime. Yeah. Okay. So this is not true. Okay. So this one means that our claim is true. Our claim is true. That means alpha prime at t is like alpha prime at 0. Okay. And alpha at 0 is 0. Alpha at 0 is epsilon. So the deformation estimate shows that these after prime, they are almost the same. So that means alpha 2 prime, this is what we want, is almost like epsilon. So that's the thing. Okay. And once we have that, we can do the estimate. Okay, then we got this part. So after that, this like now we prove that we already proved that t is less than this number. Okay, we have something here, and this is what we want. We already have that. So what's next? We need to prove that this tau, the exit time, is somehow bigger than this power law time. Okay, that's again by contradiction. So you assume that this is smaller than of this one, and by definition, you immediately get this equation. Okay, and now we can estimate alpha using this. This is by definition of this is the definition of alpha. Okay, you got this one. So this means for small epsilon, you will got a wrong equation. See the right. You have a 2 lambda and here 2, but the right-hand side is smaller, much smaller order. So this is not true. Okay?
Is lambda
No. Lambda not depend on. Okay, lambda, you fix that first stage. Okay, so this is the case that just for one case. And the other case for lambda less than 4/3. The other case is basically similar, but it's just a inequality deformation transformation a little bit slightly different, but the whole thing is it's the same. It's not different. Okay. Small n. Okay. So small n, it's like we can fix it. We can choose it as large as we can. So here, let's go back to the theory. Okay. No. Yeah, the order of iteration. Yeah, but we fix it. I think we should fix it. So this procedure, we cannot push n to infinity. I think this is impossible. Otherwise, it becomes integrable. It's impossible. Okay, so we can only up to some bigger n. So any bigger n, it's okay. Okay, I think this. Okay, I'm done here. Thank you.
Forgot what is phi. What is it? What is the stability condition? Can you explain where it comes from?
Okay.
The conformal
Yeah, the phi is the conformal map.
from domain.
Yeah. So you have this is the arbitrary domain. Okay, this is a unit disk. Phi is I think phi is from here to here. Okay, so here to here. Of course, you can fix. You can see that phi will map 0 to 0. This one we can fix it. So the stability condition is 1 point vertex. Yeah, here. You only consider 1 point vertex. You see, because there is a 0 point, you can see 0 point as stationary point. So 0 point will make the 1 point vertex does not move. So you consider this one. This should be a two-dimensional ODE. Okay, you can consider this two-dimensional ODE. Is this the solution stable near this stationary point? Okay, so one is this stable, so we can calculate the eigenvalues, standard one. It's a 2 by 2 matrix. You calculate the eigenvalues, and eventually you got this. Yeah, because you see here, you calculate this part. So if this gives you eigenvalues or negative real part. Yeah, that's it.
These two ways to characterize these decision points. So you take
Yeah.
your domain, you put the point vortex, and then you follow this point vortex. So normally it's closer curve because you go back to the equation. So, yeah, because it lies on the level set. The motion of Z it lies on the level set of gamma tilde.
Yeah.
This gamma tilde is close to infinity at the bottom.
Yeah.
So you have stationary point. And then the stability means like if you start to close, you stay close. Then you can characterize the stability through the conformal map or something. That's the second level.
The stationary, you characterize.
Yeah, you can recharacterize.
Yeah.
Red line,
Yeah.
and the stability is is also characterized by the condition at this.
Yeah. So that's why he said at the beginning, so if you start with confined configurations, it depends where you put that. If you start with the blobs, you have your domain. It's not that all regions will keep the confinement.
Yeah.
Like a necessity condition is that we are close to stable. It's almost sharp.
What are the regions like? What's the picture of region that's stable? Like ellipses are stable, like what are like
Yeah. The
graphene or what? Like what's
The ellipse, it's
the ellipse is yeah.
the disk, yeah.
This is stable. Ellipse it's a state. It's
No, but you don't have the long time confinement
ellipse.
for the ellipse, yeah.
Ellipse.
No, the
Yeah,
ellipse is
ellipse.
still no, yeah, for the ellipse, very sure. Still
Oh, for the vorticity, yeah, yes. For the vorticity
Yeah.
is also for the vorticity it's open. So yeah.
I mean, the disk, yes, you have long time.
yeah, for disk, yes.
If you. No, you can perturb the disk in in a specific way. So feed triple prime.
Triple prime equals 0
to be zero.
to be 0.
These are family of domains.
Yeah.
But they do not cover the ellipse.
Ellipse, yeah.
Surprising. I mean, that what brought us to this project is actually the ellipse.
Yeah. At first wanted the ellipse.
Yeah. I couldn't believe that the ellipse cannot the result cannot be true. But I mean,
So could you describe again the dynamics of H0?
H0.
Get where the restriction on the initial data comes from.
Okay. Yeah, it's here. It's actually yeah. So this is the I mean this is motivation, how we want to describe this kind of behavior. So you see if you put two points close to each other, the other ones are very far away basically. So the behavior of the dynamics is almost it's like a two-point vortex system. So the first 2 points, they will rotate from each other, right? Like two-point vortex. It's like the third one does not affect it. Okay, relatively, I can say. Relatively, two-point vortex, these 2 points are stay close to each other, like two-point vortex system. Okay, now when you involve the third one, you see the third one will affect the motion of the 2 points, the center of 2 points, I can see. Yeah, you see it goes, it's like a circle, right? This is a solution for two-point vortex system. Yeah.
Okay, but if you consider only H0, I think that
You mean this specific H0? No. This one you mean? This one?
yeah. So what are the frequencies of
Rotation, I mean. I think this H0 is something we made it basically. So this H0, you see if we remove everything, okay, we remove everything. So what's the solution of H0? It is alpha 3. It's a constant. You see, this is a constant distance. All of them are constant distance. So the solution of this one is go back
Okay, sorry.
Yeah.
Can you
Mm.
go to the general slide? Yeah, this one.
Yeah.
Okay, you're right. H0 in this general form, omega k, alpha k.
H0, it's here.
Okay,
This
what's the shape of omega k in your example?
this one?
Yeah.
H0, you mean? This is the you think
This is
about
the
the
general,
this is in classical mechanics. Yeah, it is.
Okay.
It's a circle. It's not a case of point vortex. Okay, this is a very classical mechanics case. It's just a rotation in the phase space. Everything rotate with the frequency omega k.
What's
This
the
one.
other?
This question is, what is omega 1, for example?
Yeah, what's
In the point vortex.
In the point vortex.
The expansion by epsilon.
Yeah. Okay. This has you mean this omega?
Yeah, omega 3, we see it, right?
Omega 3, omega 1.
One.
Omega 1, it seems we didn't see it here. We didn't see it here.
But you don't use it in the proof?
No, you compute.
No,
You can compute.
you can compute, but this rotation is I think this rotation is not, you cannot see it from here. You can see you can see they are rotated because they are rotating because the distance is fixed. If you only consider H0, but in here you didn't see the frequency because it's not a classical rotation. Okay.
But if you expand in alpha, sorry.
So this is like this equation. X dot is equal to what? Minus let me think about one example. You can
You're right there, it's moonlight.
Yeah. Okay, now let me check. I have a very good example of your question. So like the frequency will depends on the radius on the distance. But I need to check.
In these questions, you have only one frequency, which is omega.
Yeah.
In this example, you have one, which is omega.
Yeah.
So only the center of vorticity rotates.
Okay.
Yeah.
So this is already after you pass to the,
Sorry, yeah,
you pass to the frame of.
exactly.
The other direction.
The other directions, you have higher order terms.
They're like epsilon.
Yeah. Higher
This is
order
for
terms.
alpha 1 or alpha 2 smallest.
Yeah, so this is for omega 1. Yeah, alpha 1 is smaller than, much smaller than alpha.
Right, so then you expand.
Yeah. So
So the first two terms are smaller than the term. Okay.
Okay, you can see this example. Yeah, this is you can see this example. Yeah. Let me see. Yeah, see this example. It's so x is like x is x1, x2. Yeah. So in this one, you can see the h is Hamiltonian is log. So the frequency here, so you can solve it. The frequency depends on the x. The frequency is like 1 over x square. If this is a square, I forget, but you calculate. It's like 1 over x. So you, but x is fixed. This is a constant. X is constant. So if your radius is small, you rotate faster. Okay. Yeah. Yeah.
You can drop the restriction on the initial theta by using a generic domain.
A general domain.
Generic sort of restriction on the domain
Okay.
to drop the hypothesis initial theta.
The restriction on the domain is a stability condition, basically. So
Because you said that
yeah.
the frequency of simulation depends on the
Depends. You want to see that? It's so this omega 3, yeah, this omega 3 depends on the boundary. Depends on the boundary. So if you have boundary, then you have you know phi, right? You know phi. And then you expand phi as you can extend phi as 0. So you have something like a C X N. expand zeros, and the omega will depends on some n. It depends on C0, C1, C2 after that, if I remember it. So omega will depends on the C0, C1, C2. The first, yeah, the up to second order, I think, up to second order. So once the domain is fixed, then omega will be fixed. This can be explicitly calculated again, but I didn't put it here. But it's a little bit long actually. Mhm.
Expecting that the generativity of the initial data,
Mhm.
you have to impose it to some non-resonant condition.
Non-resonance condition. So here.
To do Birkhoff normal form.
Ah, okay. Here we don't need to that. We don't need to do that because it's like if you go to classical one, yes. Yeah, classical one because it depends on how many n you have, right? If n is 1, then there's no resonant like the resonant condition, I think. If you only have 1 point, if you have 2 points, then you have the diaphonic condition to satisfy to solve the equation to do the Birkhoff normal form, right? Yeah. But for us, I think no. For us, the answer is no. Because for us, the only trouble which can generate the resonant or we can say the diaphonic condition is this one omega. But now we only have 1. You see, we only have 1. It's like we only have 1 term. Then it's not.
So if you want to study 4-point vortex, you will have.
No, still, if we study higher more points, 4, 5, you have logs, more log, but only have 1 quadratic term. Yeah.
We need to assume that one distance is dominant.
Yeah.
There's a second dominant. This is the type of configuration that we have. So yeah.
So you have only one which is distant to the other.
Exactly.
Yeah, that's the center of vorticity.
Okay, thanks.
But the first result, as he mentioned, so the first result is like the standard normal form. So you have to exclude 0 measure initial data to get the long time.
Yeah.
That was the first result.
Can you go to the theorem too?
The first, I think it's here. The Birkhoff normal form.
For your.
So from the one that we just see now, it was not the current problem. The sigma of alpha K and alpha K.
That was
just the general stuff.
Yeah, that's a general.
This is the theorem.
Yeah, there's a theory.
I'm sure I understand.
But this one is also like a long time and you have to. But what is the generation? Is there generation?
In the first one, this is the first result.
This is this one that you just put.
Yeah. This is n equals 3.
Sure.
Yeah.
Can you speak a bit more about condition on the strength of the vorticity?
Second, please.
Can you say more about the condition of the strength of the vortices?
What strength of this is? Okay. So the first 2 is like because now the first 2 we consider these as relatively they will rotate each other. It's like they only see each other. So we need the center of them will exist. So we need A1 plus A2 non-zero. Otherwise, the center of this will go to infinite. Okay. And the last one is easier because it's the center of vorticity of the whole 3 points. So we need a non-zero.
This you avoid the translation. You avoid the translation.
Translation at the infinite.
In the domain here.
Yeah, we have a domain. So
But this condition avoids.
this connection just to make sure that there is a center of vorticity inside the domain.
A plus A2 is almost like 1.
Yes. Yeah, that almost like 1 potential compared to the third one.
One.
Thank you.
Développement.
Yeah, can I see the report?
How it will be put on the field's website.
Ah, okay, okay.
Yeah, it took us 20 years
sorry.
to understand, to finally implement the normal form.
Maybe we can find.
To implement the normal form.
Yeah, but it's a lot.
It's
It's a lot of steps. It's a lot of it's 10 steps of
Yeah.
forwarding.
Yes, this is what I wanted to say.
Very nice. Thank you.
There, yeah.